So welcome everyone to the second module of this course on experimental quantum optics. So the topic of today's module will be quantum interferometry. Whereas in the last module we just considered a single beam splitter. In this module we will consider the arrangement depicted on this slide, which consists of two beam splitters, here in the upper left and here in the lower right, which basically split one incoming beam into two paths and then recombine them again, followed by two detectors which are detecting this light coming out of the interferometer. So we will start by considering now a single photon Fock state going into this interferometer, and then we can ask ourselves what these detectors can detect. Well, we know from the very basics that we discussed in the last module that the single photon in the end can only be detected in one of the detectors, because single photons, well, they cannot be split into two. Yeah, so for a single measurement, we will detect the photon either in detector D1 down here or in detector D2 here on the right. However, if we repeat our measurements multiple times, then we will see that detector 1 receives the photon a certain amount of times, and detector 2 in most cases also will receive the photon in several cases. And that depends on the path length difference that we set into this interferometer. And the question is, why is this? Why it depends on the path length difference? And this can be understood in terms of interference in very much a similar way as for classical interference, because if we plot here the probability to count the photons in detector 1 or in detector 2, given by the two colors, then we will find that they depend on the path difference with a cosine square law as shown in the top here. Yeah, and this is very much the same for classical light, which is surprising because the photon, well, as we learned in the last module, can actually not be split, but it still behaves in very much the same way as classical light in such an interferometer, where it is split into two paths and then recombined. And the reason for this is can be found in quantum superposition. Yeah, if we now go through this interferometer with the framework that we discussed in the last week, in the last module, and see what is the state of the photon in different stages of the interferometer, then we will find the following. So we have our input state here, which is just a single photon Fock state as we introduced last week. If it's split in the interferometer, well, then we have a state also discussed last week where we have now a superposition between the single photon being either in path 1, upper path, or in path 2, which is the lower path, with equal probability, because we assume that our beam splitter is a symmetric beam splitter. Now, going through the two paths, one of the two photons will find a phase shift here, given by this path length difference delta L. This is just a phase shift that's acting basically on this probability amplitude to find the photon in this first path in this simple way. And if then the second beam splitter again recombines these two paths, then we will find for the probability amplitudes to see the photons either in path 1 or in path 2, that they behave as a sine or cosine of this path length delta L. Yeah? So this quantum superposition, which is the superposition of probability amplitudes of finding the photon either in one path or the other, behaves exactly like a classical interference, where it is about a superposition of a classical beam of light being in two paths of the interferometer. However, instead of electric field, now we have an interference of the probability amplitudes of our quantum state, as shown here. So, and in this type of interferometer, where what we actually do, we measure the first order coherence of the field in in a classical field, but also in non-classical light. Actually, all the interference and coherence properties of classical light are maintained also for non-classical states of light. Yeah. there will be, one can define a coherence time, which depends on the spectral width, which will then limit the path difference where you can see interference. And all this is very similar to the classical case. Yeah? So we now basically understood how this interference works for single photons and more generally for quantum states of light as an interference of the probability amplitudes. However, we would try to explain the same effect again, now using a somewhat more generic concept, which is the interference of paths. Very generally, quantum interference can appear always if a particular measurement outcome can be caused by two different paths in the experiment or two different realizations of a particular experiment. Yeah, in our interference experiment, what does this mean? Let's consider now that we have the measurement outcome that we detected the photon in detector 2. Yeah, and for this, we have two realizations of our experiments that can lead to this measurement outcome. Yeah, these realizations we call paths in this particular case. Yeah, realization 1 or path 1 is when the photon goes through the upper arm of the interferometer. Realization 2 is when the photon goes to the lower arm of the interferometer. And the measurement then is a superposition of these two possible realizations leading to interference, which depends on this path difference. However, this interference can only manifest itself if these two paths, the information which way in the end the photon could go, if they are indistinguishable in this particular measurement experiment. Yeah? As long as we cannot distinguish which path the photon went, we will see interference. In the case that we can distinguish, and here is an example where we do this by introducing also polarization, then the interference will vanish. Yeah? In this particular example, we assume now that this single photon at the input has a polarization in the plane here, which is split, and here we put a half-wave plate that rotates the polarization by 90 degrees, such that the photon after the half-wave plate is polarized perpendicular to our plane. Yeah? And that means after this beam splitter, one could distinguish by measuring the polarization whether the photon was that is measured in that moment was coming that way or the other way. Yeah? And in this case, no interference would manifest. Yeah? And therefore, interference can be interpreted as exactly this indistinguishability between different realizations of an experiment or different paths that the measured object travels through the experiment. And this concept can now be generalized also to higher photon numbers. And to do this, we look at a very particular experiment, again based on a beam splitter, where we now just have one beam splitter here. And we have two input photons now coming in the two input modes of our beam splitter, then being mixed by the beam splitter and being detected by detector 1, 2 and detector 1. Yeah? And after this detection, we do a correlation measurement. We are basically looking whether the two photons can be simultaneously detected in detector 2 and in detector 1. Let's look at this a little bit more formally. So what do we have at the input is basically a multiplication of these two single photon states, one photon in arm 1, one photon in photon 2. Yeah, if we look at the two photons individually, well, both of them have the same probability of going to detector 2 or to detector 1. And on average, we will also find that one photon always goes to detector 1 and one photon goes to detector 2. Yeah? But we will find that never there will be a correlation between detector 1 and detector 2, meaning that there is never the case that both photons actually are nicely split and one of them goes to detector 1 and detector 2. Yeah? This is called the Hongo-Mandel effect or the Hongo-Mandel experiment, which found that in these particular experiments, the two photons always coalesce in one of the outputs. Yeah, and the reason for this is exactly this path interference that we discussed before in the interferometer. If we now consider basically the possibilities that the two photons can take in these experiments, then we find that there are actually 4 different possibilities, and our superposition, our output state is actually a superposition of exactly these 4 possibilities. Yeah? What we can have is that the photon coming from here is transmitted by the beam splitter, the photon coming from the left is reflected by a beam splitter where it gets a phase shift of pi over 2. Yeah? So there, this I here. That's possibility number 1. Possibility number 2 is that both photons actually are transmitted. Yeah, nothing is reflected here, so therefore there is no phase shift. The third possibility is that both photons actually are reflected, yeah, where both of them are getting a phase shift, and that's why we assign a minus sign to this possibility. And the last possibility is that the photon coming from the top is reflected, and the other one is transmitted, again with 1 phase shift because we have 1 reflection. Yeah? And if we see now these 4 possibilities, then we will find that 2 of them, the middle 2, well, they are indistinguishable, because in a measurement, if the 2 photons had the same properties, then one cannot distinguish whether this possibility is realized or this possibility is realized. Meaning these 2 possibilities can interfere, and now we can see, due to this phase shift, due to reflection, these 2 possibilities actually have different sign, which means that they are interfering destructively. Yeah? Which means in total that this realization of the experiment, both photons going out at different paths, never can be realized. Yeah? Leading to the output state shown here, that we either have 2 photons in the first mode or 2 photons in the second mode with a certain phase shift. Yeah? This is the same concept of path interference that we discussed for the interferometer before, just now here used for 2 photons.